Hi Sanjay, how are you? Am I audible, Sanjay? Okay. Let's wait for a few more minutes, okay? Let's see if others are joining. Then we'll proceed. Okay. Okay, fine. Let's get started. So we'll just try to continue from where we have left. So in the last class, we were simulating a part of a separation plant. We only simulated the liquefaction cycle. So today we'll be simulating the distillation section of the plant. Okay. So I hope you have the Aspen file which we have worked in the past. You can either continue on the same file or you can just create a new file because this is a completely different segment. So today we'll be working on a distillation, right? So yeah, fine. So before just going there, I want you to just keep your Aspen ready. Meanwhile, I have few questions. So, so can you just answer this question? What are the typical operating pressures of Haber's process? Just put it in the chat box, or you can unmute your talk. See, I guess you're only two, so you can we can have much more interaction than what the usual. Okay. Can you answer this? What are the typical operating pressures of Haber's process? It's about typically about 200 atmospheres. Okay, so the answer is C for us. Okay, it's between 100 to 400 bar. Fine. And next, so here we have a simple figure. Okay, just it has got one inlet stream S1 and outlet stream S2. Okay, now for this particular case, can you tell me which block are we discussing about? The block B1. Seeing the options which are required for the input. Can you tell me which block are we talking about? or which of the model pellet in Aspen requires this kind of inputs. What about Vinay? Vinay, is this your first session or have you been before? Am I audible, Vinay, to you? Okay, fine. So the right answer is it's the heater, right? So it's asking you what is the heat duty. It's asking you what is the pressure, outlet pressure. So it's the heater or the cooler block. Okay. It has got other inputs like temperature, temperature change, degree of superheating, etc. Let's read the required inputs. So with that, you'll be able to decide which model pellet I'm discussing about. Okay, fine. So for this particular case, can you tell me what the relation between temperatures of stream S1 and S2 by viewing the data over here, whatever the data is given. From this, can you tell me the relation between temperatures of stream S1 and S2? So why do you think it's less? Can you tell me why do you think it's less? Either, I mean, Sachin and Sanjay. So if you are removing heat from a stream, then your outlet temperature will be smaller than the inlet temperature, right? So here the question is asked: the temperature of stream S1 is greater than or less than S2, right? So in case if you are removing heat, that means your inlet will be at higher temperature, right? That's what I know. Both of you are saying you are removing heat from the system. That means your outlet temperature will be smaller than the inlet temperature, right? Just read the sentence once more. Fine. Anyways, so can you tell me the full form of TENA? Yes, it's correct. It's Tubular Exchanger Manufacturer Association. Great. So both of you, I think, both of you are following the lectures very nicely. It's good to know. Fine. So see, I have one question. So this question, I expect you to perform a simulation. Okay. So here we have air. Just to continue from where we stopped, we were trying to simulate a separation plant, right? So this is the plant which we are trying to simulate. We have simulated this section. Now today's task is to simulate the distillation section. Okay. This is what we are trying to simulate. Now I'll read out your question. It's given air. The composition is given, which is at so and so temperature, 6 bar, with a flow rate. Basically, the stream conditions are completely specified. Okay, is sent to the bottom of HP column. In this case, you have two columns. You see this one bottom column, top column. Both are different columns. Okay, it's not a single column. You have two columns in this setup. The question asked, air is sent to the bottom of HP column at the bottom stage. Do you see this? The one which is entering near the bottom of the column. That's what it refers to. Okay. This bottom of this column has got 9 stages, a total condenser, distillate molar flow rate of so and so value, and a reflex ratio of 2.1. Neglect the pressure drop in the column. Okay. Now that's the column specifications which are completely specified. Now both bottom product and top product of HP call are expanded in throttle valve to 1 bar and sent to LP call. Okay. You see this bottom product is just expanded through a valve and sent to this call. Similarly, this is also expanded. There's no throttle valve over here. Probably they forgot to put. Uh, expanded and then sent to the column, top column. Sorry. Okay, sent to the top column. This low pressure column has 39 stages. It doesn't have a condenser. The boiler ratio is given to be 0.65. Okay, and the bottom product of HP call is entering on the 15th stage of LP call, and the top product is entering at the first stage of LP call. Okay. Neglect the pressure drop in the column. So basically all the specifications required for the distillation column simulations are given. So using this data, can you simulate this? Can you simulate the process? And can you tell me the condenser and reboiler heat duties? Could you get the question or shall I repeat? Could you follow Sachin and Sanjay? Okay, fine, no issues. See, we are simulating this section of the process. Okay, it has got two columns. One bottom column, which is also called HP call, and the top column, which is also called LP column. Okay, given that air with the composition at a certain temperature with a pressure of so and so flow rate. That means all the stream specifications of air are specified. Okay, completely specified. It's sent to the bottom of HP coil at bottom stage. Do you see this? It's sent to the bottom of HP coil. Okay. Now we require some details about the column for simulating the distillation column, right? So distillation column has got 9 stages. It's a total condenser system with a distillate molar flow rate of so and so and the reflex ratio of so and so. Okay, all the specifications required to simulate HP column are given, and both the bottom product and the top product of the HP coil are expanded to throttle to 1 bar and then sent to LP coil. Okay, which means the bottom product as well as the top product. I think this is the one which it is referring to. Both the bottom product and the top product are taken through valves, expanded to 1 bar, and then sent to LP call, which is top one. Okay. Now, what about LP call? LP call has got 39 stages. It doesn't have a condenser. It has a boil-up ratio of 0.65, and a bottom product of HP call is entering on the 15th stage of LP call, and the top product is entering at the first stage of LP call. Okay? Which means all the specifications for LP call are also given. Now I want you to calculate the heat duties of condenser and reboiler in this system. Can you do that? Now is it clear? You can either use the previous file or you can create a new one in case if you don't have the old one. Okay, it doesn't matter. If you have the old one, you can just continue with that. In case if you don't have, you can create a new one and then try doing it. Okay. So I'll be just keeping this question. So in case if you have any queries and all, just unmute and tell. Okay, because I won't be able to follow the chat box. So just unmute and just talk whatever you have done. Okay. Arey, in between, keep posting your status, okay? So that I'll also know where are you. Right? Both Sanjay and Sachin, just keep posting your status. Where are you? And yeah, fine. Just continue, keep continue. Guys, can you tell me your status? Where are you? Column two. What about Sachin? Valman. Okay, please continue. So, Sachin, about the condenser and reboiler pressures, in the question it is mentioned, to assume your pressure drop in the column to be zero, right? So, whatever is your feed pressure will be the condenser and reboiler pressures. Okay, you assume the same as the feed pressures. Okay, Sanjay. I'll wait for Sachin to answer. Then I'll see the values. Okay. Thanks. Do the second problem also. The second thing, right? And then just continue with it. Uh, just check your conditions, Sachin, because Sanjay has a value over here, right? So you might be giving some input error. Just check it. See, if we are using Kelvin scale, temperature can't be negative. Okay. However, if you are using degree centigrade, it's fine. It can be negative. Just check the units, which units you are using. So you're able to do, right? That's good. So can you continue the second part of it? Now vary the boiler pressure of LP coil to match the condenser and reboiler heat duties, which means the condenser of column 1 should match with the reboiler of column 2. Okay, so the value of 29438 must be equal to 30121 by changing the boiler pressure of LP coil. Can you just match both of them? You're able to get some answer for that, matching the condenser and reboiler heat duties. Sanjay Sachin, can you please respond? Are you able to do the second part? Okay, Sanjay, please do it. Please save your file in between, okay? Guys, can you tell me your status? Where are you? Okay, Sanjay. Sachin, what about you? Okay, fine, man. I'll also start doing parallel. Okay, it's 7 o'clock. So let's see. Then the first thing which you're supposed to do is give the components and then go to simulations. So here the question it said two columns, right? So let me put two columns. Right, so this is my HP call and that's my LP call. So let me rename. Uh, uh, Guys, do let me know in case if I'm making any mistakes. Okay, it's possible that I may give some wrong input and finally it won't come. So 163.7, right? And it's got has got the molar flow up to 50. Then we have mole fraction of nitrogen, so 7.1 to 0.0093. And then HP call has got 9 stages. Total condenser, the total condenser, distillate molar flow of 30, reflex ratio of 2.1, we onto the bottom stage, which means it's ninth stage, right? Ninth stage, pressure the same as inlet, 6 bar. So here we need pressure changes, two valves. We need another steam. Let me just put this as water and this as top. Okay. So keep saving your file in between. Okay. Then LP call. What are the inputs we have? It says 39 stages without a condenser. None. Right? And what else is given? Boil up ratio is 0.65. Right? The bottom product of HP call is entering on 15th stage. Bottom product is entering on 15th stage, and top product is entering on first stage of LP call. Pressure is currently right. So that's all we need to give input. Let me run this. Yeah, we have some results. Let us see the condenser and so heat duty of condenser. I think Sanjay has specified some of the values. Okay, it's in calorie per second. Right? Let me change it to calorie per second. Okay, yeah, I think I too got the same value, Sanjay. That's great. Fine. Now, so Sanjay and Sachin, you are able to do, right? I'm sure Sanjay has got the correct one. What about Sachin? Sachin, you are able to do? Fine. The second part says vary the boiler pressure equal to match the condenser and reboiler heat duty. So, if you disturb this one, the only value which will change is the reboiler heat duty, right? However, the condenser value of LP remains the same. So, what we can do is just copy paste the or just go to design spec. So we'll say Q reboiler, Q condenser. Okay. So which reboiler are we talking? We want the reboiler of LP call, right? Yeah. Calibrated reboiler heat. Uh, Condenser of is HP call, right? So we want to specify QR plus QC must be 0. Okay, that's our tolerance. Just recheck if you have given correctly. Then what are we varying? So in the question it said a vary boiler pressure of LP call, right? So we'll vary block variable, block call LP call, boiler pressure. Did I miss that? Which one are we supposed to vary? LP call. What did you search for? Okay. Yeah, yeah. Specified molar boiler pressure. Okay. Thanks. So let us put limits as zero point 0.5 to zero point 0.8. Just I guess. Let us run this. Fine. So we have some results. So the value is 0.62. Let me just reconcile them. Deactivate this design spec so that I'll have a proper simulation. That's all. So which means these two things are thermally connected. Okay. As you see that this, as you see, the duty of condenser and the reboiler are the same. So these two can be thermally integrated. Okay. So that's what happens in an air separation plant. If you see here, two columns, these two are thermally linked. Okay. So it says the condenser slash reboiler, right? So both of them are into one heat exchanger, which is called as condenser reboiler and a combined heat exchanger system. So that's what we try to do over here. So condenser of the bottom column will act as reboiler of the top column. Okay, thus they will be thermally coupled. Fine. So yes, that's great. So yeah, you are able to do this simulation properly, right? Good. So do you have any questions? Or do you have any specific questions which you want me to discuss in the coming weeks? We have three more classes, if my guess is correct. This is ninth week, right? Yeah. We have three more classes. Do you have any specific things that you want me to discuss? Yes, Sanjay. Okay. See, in the second part, what are we asked? Vary one of the input to the LP call such that you have same heat duty for condenser and reboiler. Okay. So what did we do? We use design specification options which is available in Aspen. So we said we told design spec saying we defined heat duty of reboiler, heat duty of condenser. We told both of this should go to 0. Since one is positive value, another is negative value, so its sum should go to 0. By what should be vary to get it? will vary the molar boil-up ratio, which is asked in the question, which is a block variable. So basically, we are defining each specific element which we want to vary and which we want to make it zero, and then ask it to simulate it. So that's what we are trying to do. Okay? Essentially, the aim is to have the condenser and reboiler heat duty to be same so that they can be put in one heat exchanger instead of having a heater and a cooler. You see, the condenser is a cooler and the reboiler is a heater, right? So instead of separately having a heater and cooler, we can have a combined heat exchanger which will help us in heating and cooling. Okay, that's the main idea of having this combination of condenser and reboiler. Okay, now could you follow Sanjay? Okay, great. You have any specific thing you want me to discuss in the coming weeks? By the way, when is your exam? April 30. Okay, so we have 3 more weeks and 3 more sessions. Fine. What about you, Sachin? Do you have any specific things to discuss? See, if question comes from you, it will be easier for me to pick up the concepts. Okay, so the exercise which we started, the simulation of air suppression plant, is almost complete. All we need to do is just put all 3 days work together and in one flow sheet, and that's how simulate it. Uh, I was thinking in the coming week I'll start another problem which includes this design spec optimization and so and so. So in case if you have any other things which you want me to discuss, I'll start those. Uh, Simulate assignment 8 part B. Okay, I'll go through it, such. So, in case if you have any specific things, other than if you don't have, then I'll proceed with optimization and designs with one more problem in the coming week. Okay, is that fine? Can we do an optimization and design spec problem in the coming week? It's an LNG process. Okay, it's similar to air suppression plant. Whatever we did, it's from an industry. So you'll have all data from industry only. Whatever I have given similar to air suppression. And by the way, this data is taken from an industry. Okay, so it's not a synthetic problem. Okay, yes, we in fact we have one problem based on reaction as per the schedule. Okay, so that anyway we are going to solve one reaction system. Any other things which you want me to discuss today? Sachin, I'll go through this question. Okay, I didn't see this question. I'll come back. So if not now, then in case can we meet the coming week then? Okay, fine. Then have a good week. See you coming.